Welcome to this video lecture, the Introduction to Gas Piston Engines. This video will explain the 4 different types of gas piston engine applications. They are the 2-stroke and 4-stroke gasoline piston engine and the 2-stroke and 4-stroke diesel piston engine. Starting with the 4-stroke gasoline piston engine, there are 4 strokes of the piston to complete one duty cycle. On the intake stroke, air and fuel enter the combustion chamber. Next comes the compression stroke, for which the air-fuel charge is compressed to before top dead center piston position, and at that point a spark ignites the fuel air charge, releasing combustion energy in the form of pressure exerted against piston area to create dynamic force to the power stroke. And then the next stroke is the exhaust stroke. The crankshaft is connected to a camshaft which rotates at 1/2 the RPM of the crankshaft. The camshaft, its function is to open and close the valves using cam lobes. The maximum rated brake horsepower will be reached at the middle range of RPM on the 4-stroke gasoline piston engine. Next is the 2-stroke gasoline piston engine. After the engine starts, the downstroke will represent the air and fuel intake, the power, and the exhaust, all on one downstroke. The upstroke will be the compression of the air-fuel charge and its ignition when the piston is at before top dead center by a spark igniter. The 4-stroke piston engine will go through 2 revolutions of the crankshaft for 1 power stroke, whereas the 2-stroke piston engine will have 1 power stroke per 1 revolution of the crankshaft. With the 2-stroke piston engine, the gasoline must be pre-mixed with 2-stroke oil at the ratio of 1 US gallon per 4 ounces of 2-stroke oil. Since there is 128 ounces to 1 US gallon, and there's 4 ounces of 2-stroke oil added to 1 US gallon of gasoline, the ratio of 2-stroke oil to gasoline is 128 to 4, which reduces down to 32 to 1. 2-stroke oil to straight gasoline mixture ratio. This is the ratio between the 2-stroke oil and the straight gasoline. You cannot use straight gasoline in a 2-stroke piston engine because the fuel itself lubricates the engine, and it is required to be mixed with 2-stroke oil before it is delivered into the fuel tank. There's no standing motor oil like there is on the 4-stroke gasoline piston engine. The 2-stroke piston engine will reach its maximum rated brake horsepower and torque at maximum RPM. As a matter of fact, the correct way to operate a 2-stroke gasoline piston engine is to operate it at maximum RPM at all times, because higher RPM equates more lubrication of the crankshaft, piston rings, and connecting rod, as well as increased airflow through the cylinder for cooling. Next is the 4-stroke diesel heat of air compression piston engine. There's 4 strokes of the piston to 1 duty cycle, except on the intake, only air enters the intake stroke. not fuel. This air is then compressed to heat of air compression pressures, increasing the temperature of the air sufficient to ignite the fuel, just like with the gas turbine engine. The typical compression ratios of gasoline piston engines is around 10-to-1 compression ratio. But on the diesel piston engine, the typical compression ratios are 23-to-1. So with that type of extreme compression of the air, the temperature will rise to ignition temperatures. Only on startup there will be assistance with a glow plug to help heat the air with the heat of air compression. But instead of a spark at before top dead center, there will be fuel injection of diesel fuel. You have to remember that on high compression heat of air compression engines, such as diesel and turbine engines, a slow burning, hard to ignite fuel must be used. Gasoline is so volatile that it instantly goes from liquid to gas in open air due to its high volatility. But kerosene jet fuel and diesel fuel are very similar in the sense that they are not very volatile in open air, and in order for them to ignite, they require extreme amounts of heat of air compression to do so. Gasoline piston engines with higher compression require higher octane. Octane has no connection to the amount of energy in gasoline. All that octane does is it slows down the speed of the gasoline fuel when under higher compression to prevent explosion of the fuel, also known as detonation or commonly referred to as knock. Newer automobile gasoline piston engines have anti-knock sensors, allowing even low octane gasoline to be compressed in higher compression engines. That is a technological breakthrough. But traditionally, octane has a lot to do with how heat of air compression engine fuel works, because kerosene and diesel are basically the same type of fuel. Kerosene is used on gas turbine jet engines because gas turbine jet engines operate by heat of air compression just like diesel piston engines do. So a hard to burn, slow burning fuel like kerosene, jet fuel, or diesel are used in diesel and gas turbine engines. Once the engine lights off and fires into operation, the heat of air compression is sufficient to raise the temperature to ignite the fuel. So for any combustion to happen, you need oxygen. Air is 20% oxygen. You need heat, so you get it from the heat of air compression at 23-to-1 compression ratio. And then instead of a spark, you will have fuel injection of a slow burning, non-volatile fuel like diesel or kerosene jet fuel. The maximum rated brake horsepower and torque are reached at very minimum RPM due to the fact that the pressure on the piston head is so much greater than with a gasoline piston engine. Pressure times piston head area is equal to dynamic force, so the force on the piston is much greater in the diesel than compared to the gasoline. Therefore, the torque and the brake horsepower are much higher at lower RPMs. This makes the diesel 4-stroke piston engine ideal for semi trucks and high payload vehicles that require high amounts of torque at low RPM. With the right transmission system, a 4-stroke diesel piston engine can still move a heavy vehicle to high speeds in which very high torque exists at very low RPM. Lastly, we have the 2-stroke diesel piston engine, which, just like the 2-stroke gasoline piston engine, the downstroke is the power, air intake only, not air and fuel intake, and exhaust events happening on the downstroke. And the upstroke is heat of air compression and fuel injection. A two-stroke diesel piston engine can reach very high brake horsepower, torque, and RPM all at the same time due to the fact that there is a power stroke per 1 revolution. In terms of lubrication, the two-stroke diesel piston engine could use its own separate oil supply or could tap off some of the diesel fuel in the fuel tank, mechanically pumped into the crankcase in order to support lubrication of the piston rings, piston, crank, and connecting rod. One more note about the 4-stroke diesel piston engine is that the oil that lubricates its crankcase cannot be standing or static. It has to be dynamically moving out of the crankcase to an oil cooler, which is an oil radiator, and then brought back into the crankcase. That is because the heat and pressures are so extreme on the 4-stroke diesel piston engine that simply allowing oil, 4-stroke motor oil, to sit in a crankcase would potentially cause it to gel up and seize the engine. With the 2-stroke diesel piston engine, since it has the maximum brake horsepower, torque, and RPM for the given weight compared to any other type of engine, this is very ideal to use for high performance, low fuel efficiency applications such as drag racing, and also these types of engines are used on model airplane gas engines. They have the glow plug and the startup as well, but the power to weight ratio of the 2-stroke diesel piston engine at, let's say, 23:1 compression ratio is comparable to the gas turbine engine, but without the high cost of the expensive materials of gas turbine engines. So if this type of engine was scaled up, it could be used for very high performance aircraft that rely on piston power driving a propeller or a fan with comparable power to weight ratios as the turbine engine, but to a limit. But still, there is always going to be a higher power to weight ratio with gas turbine engines compared to any type of piston engine application. So these are most common on the model airplane glow engines because those might be 2 to 3 ounce engines putting out 2 pounds of propeller thrust at 15,000 RPM. So that's just an example of the type of power in terms of both brake horsepower and RPM you can get back with a 2-stroke diesel piston engine. So the overview for 4-stroke gasoline piston engine is air and fuel intake, compression, ignition power, exhaust. With a 2-stroke gasoline piston engine, downstroke is the power, air and fuel intake, and exhaust. Upstroke is the compression and ignition. 4-stroke diesel heat of air compression is air intake, heat of air compression, fuel injection, power, and exhaust. And the 2-stroke diesel piston engine is power, air intake, exhaust on the downstroke, heat of air compression, and fuel injection on the upstroke. Thanks for watching this video, and have a good day.